Hello guys, welcome to this edition where we shall be learning on how to use the GIMP to process space images. Previously, I talked about how to use Photoshop to process space images. I used images from the Hubble Space Telescope. I also used images from the Las Camas Observatory and the James Webb Space Telescope. In fact, I did a lot of extensive talk. I gave introductions of the theory behind image processing. I'm going to refer you to that part later in this video. But in this part, I'm going to be focusing on how to use the GIMP software to process images from the Las Camas Observatory. We're going to be focusing on the Las Camas Observatory, and I'm going to take you to our website, www.paxskilab.space. So follow me to this website. Welcome to our website. This is our official website, passkilab.space. You can see how beautiful it is looking. You can read down, you can register, you can read down to understand our projects. But I want you to follow me to the project side. Then from project, you will see our primary projects. Now go over to Astrophoto Visual Development. Then in Astrophoto Visual Development, you will see this page. Then here are the instructions. Here are the instructions. You can read that instructions, but for now, I want you to go over here to download Fit Liberator. If you click on it, it will take you to the page where you will download Fit Liberator. You can take your time to read all of these things, but I want to go straight to the point. So to download it, you come over to NOLAB Application Archives. Then you look for Windows. You download for Windows. After downloading it, go ahead and install it. The installation is very simple. Then I'm going to go back. So if you click on GIMP, it will take you to the website where you will download it. And here is the website. You come over here, download the latest version. So going back, so if you continue to scroll, you will see the videos that I've told you that I made on Photoshop. There are about 12 of them from lesson 1 all the way to lesson 12. And I talked about how to use Photoshop to process images even from the James Webb Space Telescope. And it is worth exploring. And below it, you see for GIMP, okay? And then after you have learned how to process your images with either the GIMP or the Photoshop, you come over here to check the table of popular galaxies, nebulae, and star clusters that can be observed from January to December. Right now, this is March. I'm recording this video on March. So these are the objects that are observable with a large Camas observatory or even with your own telescope. Okay, like for instance, this is the Andromeda galaxy. If you want to take images of the of this Andromeda galaxy with the Large Camas Observatory, you can do that. Orion Nebulae, these are very beautiful Pleiades, very beautiful structures in the sky that you can process. So I'm going to refer you. I'm sorry. After processing your images, you can share your images with us, so we can update our website. We can always publish it here, and also you can post on your social media handles. So I'm going to take you to this video where I talked about the theory behind image processing. I mean the scientific theory behind image processing, so that you can have the full knowledge before we move over to the real part, which is the work. Thank you for listening. So the bedrock of our program today is on astrophotography image processing. So astrophotography image processing is simply, learning how to combine images of space telescopes or ground-based telescope to produce beautiful images. So before we go into that, we would like to acquaint ourselves with some of the terminologies and technologies used, and that would bring us to our table of contents. So we're going to learn first of all what filters are. We're going to learn types of filters, CCD, and telescopes, requirements, and basic steps. So what are filters? Filters are devices that modify the light entering the telescope eyepiece either by blocking certain wavelength or by enhancing specific colors. They are useful for astrophotography because they can reduce light pollution, increase contrast, and reveal faint details and create artistic effects. Filters, when you are taking an image of a particular object in the sky, you have light from different sources, and all this light end up saturating your images, and that's not fine. So we use filters to block some of those unwanted light sources from entering our telescope or from entering our telescope. So types of filters, we have narrow band filters and broadband filters. These are the major filters that we use in astronomy. We also have solar filters and so on and so forth, but these are the ones that we concern us for the purpose of our lesson. So broadband, or you call them wideband filters, are designed to transmit a wide range of wavelengths, such as visible spectrum or the infrared spectrum. They are used to capture natural colors and details of celestial objects, such as planets, stars, galaxies, and nebulae. They can also improve the sharpness and clarity of images by reducing atmospheric turbulence and chromatic aberrations. And we have examples of such kind of filters. We have the red, the green, and the blue. They are normally called RGB filters. So look at the kind of filters. So if a white light is incident on this filter, it removes the other colors and allows the red to pass through. The same thing with this one, the blue filter and the green filters. Also remember that these are the primary colors. So if you combine them in the right proportion, they would give you white. And these three colors are responsible for most of the colors we see in our daily lives. So the combination of them would give us different colors. So that's about that. Then we have the narrowband filters. Narrowband filters are designed to transmit a narrow range of wavelength, usually corresponding to specific emission lines of gas, cloud in space. They are used to isolate and enhance the contrast and color of certain features such as hydrogen alpha, oxygen 3, sulfur 2, and nitrogen 2 regions. They can also reduce the effects of light pollution and moonlight by blocking unwanted wavelength. And these are examples of such filters. This is hydrogen alpha, hydrogen beta, oxygen 3, and sulfur 2. And these filters are mostly used in observing regions of nebulae or star forming regions because the three elements mentioned here are the building blocks of these regions, like these stars. And if you observe very well, the hydrogen alpha is red, it's red in color. Sulfur is also red, but a different shade of red. And the oxygen 3 is in cyan, a little bit of greenish, blue and green combination, so we call it cyan. And this is better, hydrogen better. So for instance, if you combine the colors from these three elements that I mentioned, which is the sulfur, the hydrogen, and the oxygen, like these are their colors. If you combine them, the result would be this. But this is not good or ideal for visual illustration because there's no much difference between the sulfur and the hydrogen. So to be able to distinguish between these two most especially, we need to reassign them to a different color so that we can distinguish them. So for that, and the oxygen being the one that has the highest frequency or the lowest wavelength, we assign it to the blue color. Okay, then hydrogen we assign it to the green color, and the sulfur we assign it to the same red color. And so when you combine these three colors, you would have this beautiful image. And this is very good for visual illustration. At least you can see region where there is much sulfur or much hydrogen or even oxygen. And this brings me to an important question. Sometimes some of our participants ask me some important question. They'll, they'll ask questions like, assuming that I were to be at these points in the universe, will I be able to see these objects in this form? And my answer is no, you won't be able to see it in this form. You would see it in this form. We are just using this for visual illustration, at least to map out some visions where a specific gas is much dominant. So this does not really give you the information about the gases, and the elements present. So we have this technology called the CCD. A CCD, meaning charge coupled device, is a type of sensor that converts light into electrical signal. It is often used in cameras or telescopes for astrophotography because it has high sensitivity, low noise, and good dynamic range. So a CCD camera can either be color or monochrome. So, for instance, the commercial cameras that you have or your smartphone camera are made up of this color CCD. So they give you the color of the object in real time. You don't need to take the pictures in gray or in RGB and combine them later. As you are focusing on that object, you are seeing the color in real time and you take the picture. So it doesn't really take much time. Then we have the monochrome. This is the one we use mostly in astronomy. Okay, this is the one you use the broadband and the narrowband filters with. So this is an example of that filter here. So this is the CCD. This is the whole CCD component, and you see these filters of different colors mounted on it. So observe what is going to happen as white light from a source enters it. The filters breaks it into different colors, and then you have these heaps of pixels. By the way, this CCD converts the pixels to the computer language, which is in zeros and ones, and an end result is what you will see now. And here's the result. So that is the work of a CCD in a camera or a telescope. So for the purpose of this lesson, we shall be using images from the Hubble telescope, the Webb telescope, and the Las Cumbres Observatory. You can use images from different places, but what I'm going to teach you here will serve as the basics into image processing. So here are the cameras of the Hubble telescope. We have the wide field and planetary camera too. There are 45 filters in this camera, but this is the old, it has been changed with this new one, which is the wide field camera 3, which has 62 filters. We have advanced camera for surveys, we have the near infrared camera, a multi-object spectrometer. So in total, you have about 145 filters, but the unique filter is up to 100 because some of these filters repeat in some of these instruments. Then we have the James Webb Space Telescope and some of the filters. And in total, we have about 29 filters, but a head count of the filters would give you 26. The reason is because some of these filters repeat in some of these cameras or instruments. So, some examples of filters you would see in the Hubble Legacy Archive, we shall see that in the future, are F502N and F606W. The F prefix indicates that they are filters, yes, while the N and W suffixes denote narrowband or wideband respectively. So other types of wideband filters you would see are these. Sometimes you would see this M, LP, and X. These are also wideband filters, okay, but they are a kind of experimental kind of filters. So M denotes medium, LP denotes low pass, and X denotes experimental or custom. We're going to see that as we proceed. Filters are typically labeled according to their wavelength in nanometers. In the RGB color model, red light has the longest wavelength, of course, and followed by green and then blue. If you want to colorize your space image in RGB, you can assign filters to appropriate colors as follows. So for instance, if you have a particular object in the sky taken with these different kinds of filters, which one would you assign blue, green, and red? So the one that has the longest wavelength indicated in these numbers here, we go to the green followed by, sorry, we go to the red followed by the green and lastly the blue. For instance, if you look at these filters, maybe they were used to take image of a particular object and you are looking for the one to assign the red color. So you would notice that 658 is the longest wavelength here, followed by 660, 656, and followed by 502. So if you want to assign these colors, this one would come as red, this one here will come as green, and this will come as blue. And by the way, this is for the narrow band filter. And for the wide band filter, and this is just a rough example, okay? So for the wide band filters, you would assign blue to the one with the shortest wavelength, followed by green, which is this one, and followed by red. So red always assume the 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 longest wavelength. So previously I was describing CCD and filters, and I said that when white light hits the CCD and the filters in the CCD, the filters separate like the kind of accept some colors and reject some colors. So so if you follow what I was actually saying, it means that if you this one was taken from the red filter, this image was taken from the red filter, and this is taken from the green filters, and this is from the blue filters. But in reality, that is not what happens. In fact, these filters actually remove all the colors from the image and only show shades of gray like this. That is what happens in reality. So when you are using these RGB filters, you have these gray images. You don't have them in this form. So we input these colors with our computers when we are trying to process them. So when you color this one with red in your computer, you color this one with green and this one with blue, and you combine them, it gives you the real color of the object. So it is not this way when you are collecting it from the observatory. When you're collecting from the observatory, they will look like this, gray. So when you come into your office to process them, you are the one to add those colors. So this is exactly what is happening. So the requirements for you to be able to process your images are you need Fit Liberator. It's a program that helps to convert your fit files to TIFF files because we are working with, like in astronomy, we're really working with fit files. So it helps us to, this program called Fit Liberator converts our images from fit to TIFF. And we can also use it to stretch our images. Then we have Photoshop. I'm going to be using this Photoshop in the meantime. Then we have PixInsight, GIMP, and SalsaJ. We have numerous other programs, but I will be limiting myself with Photoshop and GIMP and SalsaJ in the future. So the basic steps are, once you've downloaded your images, that's the first thing you should do is to stretch it. To stretch it, then you add the colors, and after adding the colors, you will clean it up. You clean up your images, and in this cleanup, it involves removing some pixels that are not supposed to be there. Okay, some pixels that are not part of the image, and also you enhance some part of the image to bring out the details. But one important thing I want you to know is that images from these telescopes have been stacked and calibrated. Also, images taken with space telescopes often do not have noise in them, so you don't need to worry about these. So, and that is the end. So for now, I would like us to download this Fit Liberator. I would like us to download it. So you come to your Google, you type in Fit Liberator. If you type it in, it will bring you to this Google page. Then you click on the first part. When you click on the first part, it will land you here. To land you here. So this is the Fit Liberator. It's one of the most popular program we use in image processing. In image processing, it's a very powerful program. So you can read down to see these guidelines. So, and I'm going to attach some of this link. I'm going to attach it to the description so that you would learn how Robert Hurt was able to demonstrate how to effectively use it. I'm not going to go into details on how to use the Fit Liberator. So I'm going to give you a link to the tutorial of Robert Hurt. But what I would do is to just go into the basic parts. To the basic parts, you can read down to see some other important information. So to download it, you have to click on Fit Liberator. If you click on it, click on Fit Liberator. Then I use Microsoft, so if you're using Microsoft, you can download this. And if you have other formats, computer formats, you can download these other ones. So you can go ahead to click on the one that works with your operating system. I've already done this. So once you have done that, you come over here, and once you've downloaded that, you come over here and you install it. Hello and welcome to this edition. In the previous lesson, we learned some of the terminologies used in image processing, and I also showed you some technologies like filters and CCD.R used to capture these images. We ended that section by showing you where to download and how to download the Fit Liberator, which is a program that helps to convert our fit files to TIFF files, because we need something to work with Photoshop or some of our programs. So you have to convert it. And then after the download, I hope you have installed it, but if you have not, you can install it. And after the installation, the icon will appear on your screen. So if you open it, you would see something like this. You can toggle the mode if you want the light mode or the dark mode. So I said I was going to attach a guide by Robert Hurt on how to effectively use this whole thing, the functions or some of these things. He did he made a guide on how to utilize it effectively. So in my subsequent video, I'll be making use of this to convert my fit files to TIFF files, but I didn't go into details on how everything here works, but I did make some mention of some important ones that will concern us. So, assuming that you are not an astronomer, but you love astronomy, you are astronomy enthusiast, and you would like to participate in some of these image processing activities. How would you get started? Because you don't know anything about astronomy, and you don't even know any object of interest. You don't even have any object of interest. So how would you get started? Well, I could suggest two ways. Two ways you can start to acquaint yourself with some of these deep sky objects is by using some Messier Bingo from the Las Cumbres Observatory. Let's type Messier Bingo. I'm going to attach this link to the description. Messier Bingo. So if you don't have an account with LCO or just want to play Messier Bingo, okay, let's play it. So this is a kind of object that showed you some sky object. This is M52. This is how beautiful M52 is. This is open cluster, so cluster of stars. This is M84, M86, M111, sorry, M11, M39, and 54. So you can be checking some of these things. It helps you to master some of these things. This is a spiral galaxy, M106. Assuming that you love this galaxy and you would like to process it, help of the Messier Bingo, you can just be checking some of these galaxies to see if there's anyone of interest. This one is Little Dumbbell Nebulae. All these images are in the Hubble Legacy account. You can find them there. Another suggestion I will also give you is by going on social media, you know, follow some of these pages or groups that are talking about astrophotography. Like I belong to some of them. They usually post pictures of their work on those groups. I'm just showing you an example. So this is the group I belong to, and I love they post a lot about their work. This is M82 and M81 processed by this guy. He posted it on the group, and I love it. And I said I was going to download it and process it too. This is the best way to learn to be around people that are into the activity for years. This is NGC 5128. This is the guy that processed it. So this is the best way you can acquaint yourself. Joining those groups on Instagram and Facebook, M13. But this is the best way to know some of these things. And if you need help, they are there to help you with how they were able to do it. Because one thing about this image processing is there's no particular way of handling it. Some are tougher, while some are easier to process. So look at some of this beautiful. I saw these images and I appreciate and I love them and I screenshot them and I said I was going to process them. This is M4565. It's a distant it's at a distance approximately 40 million light years away from our galaxy in the constellation Coma Berenice. It is a sign of approximately this. Anyway, so this is some of these are the best way to acquaint yourself with some of this celestial object. So in the next video, we're going to be going into the full work, into the full image analysis. We're going to image processing. We're going to start from the basic to the complex. Like I told you before, there's no particular way. Okay, many people have their own ideas. I'm going to just use my own idea, and I believe my idea is good. for beginners. Thanks for listening.